Respected faculty member, senior, juniors, and my dear friends. I, Preeti Das from MSc Mathematics 2nd SAM, feel privileged to extend my warm welcome to all presented here for the celebration of Immerse Pi Day. Before we embark on our journey today, we will begin our celebration with the spiritual invocation Saraswati Vandana, an expression of our profound reverence for the Lord. For that, I could like to invite the students of a MSc 2nd SAM. I am going to tell about the importance of a pi. It's a special day for those who love mathematics and want to honor Albert Einstein. March 14 every year is celebrated as a pi day to commemorate mathematical constant pi. The date was written in the format of month day, that is March 14, matches the first digit of the mathematical constant. It is also the birthday of Einstein, one of the greatest physicists of all time. Einstein was born on March 14, 1879. Physicist Larry Shaw was the first to celebrate 14 March in 1988 as a Pi Day at a San Francisco Exploratorium Science Museum. Pi is the ratio of a circle circumference to its diameter. This concept was first discovered in Egypt around 3000 BC. Typing pi into a calculator and pressing enter will yield the result 3.141592654, not because this value is exact, but because a calculator display is often limited to 10 digits. Pi is actually an irrational number that is often approximated with the decimal 3.14 or fraction 22 upon 7. Many mathematicians have worked over pi, calculated its digit, and applied in a numerous area of mathematics. Around 1910, Ramanujan proved that the value of pi can be written in the form of a series. Here are some fascinating facts about pi. The record for a pi reciting the most number of decimal values was achieved by Rajveer Meena at VIT University, Vellore, India on 21 March 2015. He was able to recite 70,000 decimal places. People in Egypt believed that pyramids of Giza were built on the principle of pi. In the early 70s, Thomas Langley calculated 127 decimal places pi, reaching a new record. In the second half of the 20th century, the number of digits of pi increases from about 2,000 to 5 lakhs on the CDC 6600, one of the first computers ever made. This record was broken again in 2017 when a Swiss scientist computed more than 22 trillion digits of pi. I want to conclude this speech with a quote by William L. Soff, professor of mathematical education, Brooklyn College, City University of New York. I quote, "Probably no symbols in mathematics has evoked as much mystery, romanticism, misconception, and human interest as the number pi." Happy Pi Day to all of you. Thank you.
I welcome Professor Swarup Bora sir for to give us his invited talk during this celebration of Pi Day. I'm very happy that every year the Department of Mathematics is celebrating two important days. One is Pi Day and the another one is Ramanujan Day or National Mathematics Day. So I'm very, very happy to be happy, and I congratulate our Department of Mathematics to organize this kind of event. We generally invite many scholars to give their lecture, give their talk, so that you can be acquainted with what is happening in the world, what are new things happening in the mathematical research or mathematics. Contribution of mathematics is very, very important. So I'm sure, and Professor Bora was saying that what Preeti is saying that she has studied a lot. I think all of you have already studied about the pi and pi day and everything. So pi is a universal constant, and more you know about it, more you will mesmerize about it. You cannot think about anything without pi, whether you call it as in physics, whether you call it chemistry, whether you call it mathematics, astronomy, astrophysics, anything and everything where pi is important. Without pi you cannot live, you can do any research work, okay? So I'm sure you will have a very great day ahead with you, and I'm sure you'll be having a very good, nice interactive session with Professor Bora also. I'm sure you will have a very good, discussion during the course of this day. And I welcome all of you to this Pi Day celebration. Enjoy the day, and thank you very much.
A synonyms of love transcending all spaces. Hilbert harmony. Oh, Hilbert space, where inner products sing orthogonal vectors in a synonyms ring. A treasure trove of analysis grace, infinite dimension, and elegant embrace. Banach space ballad. In the realms of math, when norms hold sway, lies a Banach space where vectors play. Complete and bound, they dance in grace. Infinite dimension, a wondrous space. Metric space melody. In metric space, distance degree, defined by the matrix with a scrutiny. Closer or distance, the point raise. Topological whispers in the spatial chase. Topology tango. Topological space where closeness defines, neighborhood and limits intertwine. Connected, compact, a topological space, infinity variety in its boundless emotion. So let us wander in a mathematical delight through a Banach Hilbert matrix might. In topology's embrace, we find a universe of space to expand the mind. Thank you.
Good morning to all dignitaries, guests, and delegates with great joy. Myself, Silpi Sikha Bora from PG 2nd Sem. It is a great privilege to read the briefing of Professor Dr. Swarup Bora sir. Professor Dr. Swarup Bora sir is currently serving as a professor in Department of Mathematics, IIT Guwahati. Sir completed his PhD from the Department of Engineering Mathematics, Technical University of Nova Scotia, now known as Dalhousie University, Halifax, Canada, 1998. Sir did his PhD on the topic, the interaction of water waves with submerged spheres and circular cylinders. Sir completed his MSc from University of Delhi, 1991, with first class. Sir completed his BSc from Cotton College, Guwahati University, 1988, with first class. Sir research areas are fluid dynamics, fractional differential equations, integral equations. Sir has over 116 paper publication in journals of high repute. Sir is also a member of editorial board of national and international journals. Sir has been working in collaboration with many national and international researchers. Sir is also a member of many apex bodies. Sir has guided 3 postdoc students and currently 1 student is pursuing postdoc under his guidance. Sir has guided 12 PhD students and currently 7 students are pursuing PhD under his guidance. Apart from this, he has also supervised many MSc, BTech, and summer interns. Sir has given over 112 invited lectures and presented in over 86 conferences. It is indeed a great pleasure to have Sir amongst us. Now I request Sir to take over the dais and enlighten us with his talk.
This we celebrate as Mathematics Day, but I think last few years people have also started celebrating Pi Day. And where is that girl who spoke? Silpi, no? Preeti. Preeti has done quite good study of Pi Day. Some of the things that she has told, there will be some repetition in my slides as well. But it's very difficult to speak to students, I think, of various background. I think you're all from physics, chemistry, maths, right? Any other subject? Okay, but I am happy that I have included some chemistry also in my slides. Okay, so I usually work, as you see, I work in fluid dynamics, I work in differential equations, and probably I am not a very suitable person to speak only about pi. And of course, when we say Pi Day, we are not going to talk about pi whole day, morning till evening. We have to talk something else. But at the same time, we have to realize how important pi is, right? So what I will try to do, I will discuss a little bit about pi, then go to certain general topics. It will not be anything specialized, because this kind of lecture, it cannot be specialized. Like she said, I have some 115 research papers. I could have simply presented 2 of my research papers here and look at all the faces, all gloomy faces. Because he may not, see, everyone is not specialized in some other area. So what I am doing, he may not understand. What he is doing, I may not understand. So I will try to keep it as simple as possible. So when you look at the title, the first page of my slide, okay, so what you see, that is what mathematician, you should be able to see more than what others see. Picture-wise, it's a nice picture, I hope. Okay. Now what else you observe? You observe a bird. What it is looking at, it is focused, right? So it's trying to see actually how I can pick a fish. Then what I see? Some rocks, but not arbitrary. You see, there is a specific arrangement of the rocks. Then you see beyond that, then if you look at this water body, it's quite tranquil, right? It's not very like topsy-turvy. Then you look at, there are some buildings. Beyond that building, it's not very clear. You can see the outline of hills. Beyond that, you see sky. So what you see here in one picture itself, you have seen nature, okay? You have seen sky, hills, cloud, water, rocks. In addition to that, that concrete jungle. I think it's a picture from either Hong Kong or Singapore, something like that. Now, as a mathematician, what you want to do? I want to see where mathematics lies. The advantage with mathematician is that you don't have to be near that specific quantity or object to do your mathematics. My special area of specialization is ocean engineering, but I never go to the ocean. I just sit in my room and do my research. Of course, when I did my PhD in Canada, I was by the shore of Atlantic Ocean. So every time I do some work, I will go and try to see actually the kind of work that are doing actually, whether it is telling with the waves that is being created in Atlantic Ocean. I studied in a place called Halifax. You may not know about Halifax, but you definitely know about Titanic. So Titanic sank off the coast of Atlantic Ocean, and Halifax was the place actually which started doing all the rehabilitation and rescue and all those things. Then when we look at the nature, and being in IIT, I am very near to Brahmaputra. Now what we see in a river, what we see in an ocean, as a mathematician, okay? When we go to some beach, I don't go as a mathematician, I go as a tourist. I want to enjoy the beach, I want to enjoy the waves that is generated there. But at the same time, we also, as being a mathematician, I try to see actually whether those kind of mathematics can be, those kind of problems can be handled mathematically. Now, Pi Day celebration, today is Einstein's birthday. He would have been 145 years probably today. So what a great thing that we are celebrating Pi Day, and that is also Albert Einstein's birthday. Though we are doing mathematics, so no one can deny the contribution that Einstein has made. People say him as the one of the greatest scientists, but I term him as the greatest scientist. So you may look at the number 1 of 73, Saris is still speaking only. I may not show you any slide even. I can just go like that. Now, I come to some concepts, not mathematical. Most of you believe in God, I am sure. In some form or other, you believe in God, okay? Especially when you find difficulty in life, you have your exam, morning you at least remember God, if not on the other days, right? And pray to God, at least give me 80% or pass me or whatever as per is your capability. Now God, you know, the capital Z, God. Then you also write God as small z, gods, that is plural. And I do not know, no one has counted probably, according to Hindu religion, how many gods we have? 33 crores. I do not know actually whether someone has a list of those 33 gods and goddesses. So for me, it's God is a concept. God is a concept like that, you rely on someone, or you feel that you think about God, you feel comfortable. You feel relieved. There is someone. You don't even know where is God, whether he is there, or somewhere else. So in that sense, you are looking at any person from whom you can get your inspiration, you can get your peace of mind. That person is your God or goddess. So I believe in God, but my gods are not the conventional gods. Having been in mathematics for such a long time, now I have worked in IIT Guwahati for more than 25 years now. Prior to that, I did my PhD, 4.5 years, then Masters, BSc. I will say once I enter BSc, then only I will say that I have started learning mathematics. Because up to class 12, what we learn, we do not even know after class 12 what we are going to do. So I have gods, not one God, because there are so many big persons who have contributed. You cannot say that scientist A, mathematician A has done more than B or C or D. We have so many mathematicians. I don't call myself as a mathematician. I say I do mathematics. Mathematician is a very strong word. Mathematicians are those people who actually we can term as gods. So I will just start with, like people start with some slok and all those things. These are my sloks. Okay? I would always like to get inspiration from the quotes that I know from great gods. These are the gods and these are their preachings, right? You know about Fourier. If you do not know about Fourier, you will not at least get a degree in mathematics and physics. Chemistry people may survive without Fourier, but for physics and mathematics you must know Fourier. Now, ultimately, that is also the picture that I showed you. It's in nature. When there was nothing, now we have everything. At tip of our finger, you get all information. You think about 16th century to think about 17th century. Well, how do you get the knowledge? You are under the open sky, you look at the sky, you see cloud, you see at night, you see moon, the stars and all those things, and that's what you try to see how the things are happening. I see a star here today, another 3 days I see the star is here. So now who is moving? The star is moving or the earth is moving or both are moving. So these are the things that came into the mind. So first study of science is definitely nature. Now Isaac Newton is considered again one of the greatest scientists the world has ever produced. And you know his contribution to mathematics, okay? Not just physics. You would not have had calculus probably if we did not have Newton and Leibniz. They were working parallelly. But even a person like him, what he says, that my powers are ordinary, only my application brings me success. There are many people with various ideas, but unless you apply your ideas, you are not producing any result, it's futile. There is no point of claiming that you have some knowledge, right? Now Gauss, another one, a great person, what he says, you can see the beauty. Basically the basic thing is that you only have the courage, because many times what happens, I tackle a problem, I find it hard, I leave it. I start another problem, I find it difficult, I leave it. But you need the courage to go ahead and you try to see that you go and complete it. So since I have come to Gauss and I will be telling more like a story, you mentioned about Hilbert space. What is a Hilbert space? Many times I will talk very light things. I am not going into the definition of Hilbert space. Hilbert was one of the leading mathematicians. I mean, you can say he is a modern mathematician. He is not of like Euler, Fourier time. He was alive in 20th century. He worked in a university called University of Göttingen in Germany for a very long time. I was fortunate enough to have visited University of Göttingen maybe in 2011 or something. Then while I stayed in Göttingen, I thought I must visit the university. It's not only Hilbert, Gauss, Weber, von Neumann. You know von Neumann, the person who invented kind of computer. They worked in University of Göttingen. I went to the library. I could see handwritten notes of Gauss and all those people. But what I'm coming to Hilbert space. Then one of the students took me to one room. It was a Saturday, I think. Then from the door he said, "Sir, you see this room." I saw in the middle there is a bust, this part, one person. I said, "What is this?" He said, "Sir, that room is Hilbert space." So like Hilbert space, when you say, it's a mathematical definition, but what they are doing to Hilbert is that it's a big room of this size. In the middle, they have a pedestal, then they have a bust of Hilbert, and they have named it Hilbert space. This is the space occupied by Hilbert. Gauss, another great mathematician. And Göttingen, actually what happens, they, like here what you see, you look at the names of the stadium, you look at the names of the roads, you look at anything, it is always mostly after the names of the politicians. Okay? This road, I will not name because people may say I am this party, that party. This road, this stadium, that university, this college. I remember one person question, this university, oh, I did not know that this person played cricket because it's a big cricket stadium named after a person who probably never played cricket in his life. In Göttingen, what they do, suppose John von Neumann was in Göttingen from 1926 to 1928. The house where he stayed, on the wall they have written John von Neumann, 1926 to 1928. You go to another house, Gauss stayed there. You go to the, we call it Sariali, to the main intersection of this small town. You see some statues. Gauss is talking to Weber. It's a picture like a statue like this. Gauss is talking to Weber, and on the pedestal it is written Gauss this year to this year, Weber this year. You can never imagine this happening in India, especially in Assam. There is a very big mathematician, Professor Jyoti Prasad Medhi, who passed away in 2017. Even many of the people working in mathematics and statistics do not know Medhi sir. But when I go abroad, I have gone to other places in India, people ask me, are you from the same place where Professor Medhi is? That's a big achievement Professor Medhi has done. We do not know Professor Medhi. Forget about having a road after him, his name or something. We don't know Professor, who is Professor Medhi. This year it is, this is here birth centenary. We are going to celebrate it in July. Bernoulli. Bernoulli says you study nature and nature is kind of what it says, acts in the simplest way. There is no double mind for nature. Nature is, that's what I said, I acted naturally. What does it mean? That it should be the usual way. Nature is not complicated like us. Nature becomes furious many times, and that is maybe due to the fault of the human being. I actually always start with this quotation. What you know about Laplace, such a big, great mathematician. What a statement he has made. It's a very simple statement. That what we know is not much, what we do not know is enormous. You talk about mathematics, talk about any subject. The way I was introduced here, people will think that Professor Bora knows everything about mathematics. No, I know a little bit. She also knows a little bit, he also knows a little bit. We cannot claim, even Laplace said that we know only little bit of whatever knowledge we think. We cannot claim, because there are many people who will claim, I know everything. That is not possible. It's not for anyone. Even Einstein did not know everything. Okay? Laplace Fourier did not know anything. So, your expectations should not be very high from me, because I follow his quote, what he says that we do not know much. So, I fall into that category. That comes the great quote of Hilbert. Okay? So, circular horizon, if you talk about, you try to focus, you come to the center. So, when you want to discuss something, you want to converge, okay? You want to converge to a point so that you can claim what you have done, and that is because you have various ideas, you have studied, then ultimately you have to converge to one idea. That means you are coming from the circle to the center, and that will be the point of view. Euler, another great mathematician, he says whatever you do, maximum or minimum will always appear. And Henry Poincare, what he has said, that when we talk about physics, we talk about law in nature, we can connect most of the nature through differential equations. Okay? Now, you can, through a differential equation actually, you can say the present state, and you can also discuss about what is going to happen in future. Now, any other law, whatever you do, they are nothing but differential equations. Okay? Then Fourier also says something, because when we talk about differential equation, you talk about, ultimately you are talking about some integration. You want to find the unknown variable by carrying out some integration, means you are introducing some integrals. And of course, we know today is Einstein's birthday, so I dedicate my lecture to Einstein. I usually do not do this kind of lecture, but when I thought, I have many lectures which I keep prepared because I have to go to many places to deliver lecture, but very few times I go to deliver lecture on a day like March 14. So I cannot simply start with some differential equation. Already Preeti Rani has given some idea about pi. I will probably try to extend some ideas or some information that I have collected. She also gave a quote. I also have that quote here. Oh, this is the one. I am starting with that quote, right? You said about it. Probably no symbol in mathematics has evolved as much mystery, romanticism, misconception, and human interest. Everything is there. It's very nice to get confused, because we are still confused about pi. Okay? You are talking about mystery, so it will be very nice, like what you are looking for in a movie. You want everything thrill, you want some love story, then you want some that people, it should be some kind of confusion and all those things. Everything is there. So pi would have been a very great movie, right? If you see, all the ingredients are there. We know the presentation of pi, but physically it is very interesting to. So I take something of length pi. Say I take a string of length pi. Now I want to say make it in 3 equal parts. It is not possible, right? It is not possible. Is it possible? It is possible approximately, but it is not possible. But you will see many physical problems, they take the length of certain things as pi. That is basically mathematical convenience. Because pi is ultimately related to what you said about circle and the radius and all those things. So it will be something like this. You have a radius, you know about a diameter, you know about a chord, then you talk about that ratio, you will get that, right? Now, up to what value? Okay, it should not be up to what we memorize. I think you have some memorization competition. I do not know how many digits you are going to tell. But most of the cases we are happy with 3.1416. Okay, we go with that. Even if you do calculator, you can do up to say 8 or 9 digit. But it is not, we know that it is never ending. But you have, when you are doing a practical problem, you have to choose a value. So you choose the value so that minimum amount of error occurs. Now, that is what I mean 3.14. See, people also 3.14, if you had not done it at 3.14, there would not have been any pi day. If you had 3.1416, you cannot describe what is that. Oh, maybe it is 14. You could have done that also, 4 o'clock in the evening. 3.14 marks 14, then 16 hours. That means he could have had the meeting at 4 p.m. Still it can be possible. He had some more digit, then you cannot convert it into any day or something like that, right? So it started long time back. Long time back it started, so that we talk about Fibonacci, Newton, Leibniz, Gauss. That means pi has generated interest not only in only in the layman. It has actually introduced fascination in many big mathematicians such as Fibonacci, Newton, Leibniz, Gauss, et al. Now they worked very hard. Now you don't have to work hard. You know what is the value of pi. Now they had to work very hard, toil very hard to see actually up to what extent the result can be extended, right? So in fact, see the last line. In fact, some of them, those mathematicians, better part of their life, suppose they are in academics for 40 years, 30 years they spend just by working on what value pi may take. Now, it is basically, it started in different ways. In Babylon, okay, so those rope stretchers, those people who were actually working with rope to measure, nowadays I don't know, they will measure with some rope, okay, 1 feet, 2 feet, like that. So they actually trying to mark the locations of building and boundaries, they found pi to be 25 by 8. So 3.125, it's not bad actually, right? It's not very far. Now Egyptians also, they found the ratio to be 3.16, if it is even closer to the value that we have started accepting nowadays as pi. Now, that was some kind of measurement. There is no algorithm associated with that. Okay? Now, Archimedes was actually the first one who actually started doing some algorithm, then by drawing some polygon, then ultimately you see what value of pi he found. It lies between 223 by 71 and 22 by 7. And most of the time in fraction we write pi as 22 by 7, right? Then Archimedes, you see when it was, before Christ, no, Archimedes was before Christ, 250 BC. Then till early 1600, people were working on pi, okay, in various countries, and they were working. Then there is one Austrian astronomer, Greinberger, he calculated 38 digits of pi by using a polygon of 1040 sides. Even if we get a polygon with 5 or 6, we get scared how we are going to deal with it. So he considered a polygon of 1040. Maybe he did not have any other work. So that was his only work, that I will try to find as many digits of pi as possible by considering as big a polygon we can do. Okay. Now Renaissance actually, that happened in Europe, it has brought implications in many areas. Not only I am talking about mathematics here, we are discussing, but it's about art, culture, literature, whatever you do, it had a very, yeah. Now, many people started working on pi. It is going on and on and on. And this is how the name pi comes. It comes actually the first few parameters of the letters of the word perimetros, which actually translate to circumference, because we know the concept came from there. Then again, 1667, Swiss mathematician Lambert, he proved that pi is irrational, and now we see the jump. 1882, Lindman proved that pi is transcendental, so it cannot be a solution to a polynomial equation with rational coefficients. It's not possible. Now, this is a very significant finding, because earlier what people thought that I could construct a square in a circle with equal area, which is called as squaring a circle, that can be done. But that pi is transcendental, okay? It showed that this is not possible, and now you cannot do for talking about this pi. Now we talk about digits. Now, pi has been calculated 31 trillion digits. I do not know how that will look like. That will be a very big number. All of us realize that. But it has been found that if you consider 39 digits, which is also very large, 39 digits if you consider, you can get the solution for a problem you are looking at involving pi, so that you don't have any problem. Now these should not be brothers, they are American mathematicians. So they say it cannot be simply that we are trying to find this value, someone else found this value, there has to be some statement, right? So what they are saying is, we are looking for the appearance of some rules. You need to find a rule. What the people are doing, all of them are doing some their own way. Okay. Now, how many digits? You see the second line. If you see a Russian sentence, whole page, okay, that can be written only by Tolstoy. No one else can do that. Without a comma, you are using a full sentence, full page, okay. Now, if someone has given, because we said 1 million digits, can you say that it is out of that pi? That we will not know unless we can say that we know exactly. We are not even, I am not being able to remember 3.1416. Beyond that, I do not know what will be that. It is 58 or something like that, right? So, pi is just not a number of fascination to know how many digits, okay, it should have after the decimal point. But it has many, many applications. So, these are simple applications I will not talk about. You know, you talk about a cylinder, you can find the surface area and volume when you see pi is present, right? When you talk about cylinder, you have this surface area, volume, okay? Then when you talk about a sphere, so this is sphere, huh? I said cylinder. So this is sphere also, you see everywhere pi is appearing. Now whether you have to put value of 3.14 or 22 by 7, that's a different issue. You talk about cone, okay? When I show the second picture to the students, nowadays they don't understand. But when I show them the first picture, oh, the ice cream, that cone that I get, so that is what your cone is, right? So nowadays I show this picture as well. Now of course radians and degrees you know. I mean, we express the angle sometimes in degrees, sometimes in radians, and when you are doing it in radian, you express them in terms of pi definitely, pi by 2, pi by 4 and all those things. You describe an arc, there also you are using pi, okay. These are some series. You see, series solution, infinite or finite, you can do mostly when it is an AP, it's a GP, or it is a HP, right? But it is always, most of the time it's very difficult. You have an infinite series. I want that you find a solution, I mean, find a convergence, I mean, the value to which the series converges. These are not following anything, right? So, but you see the values you have, you express them in terms of pi. So, I am asking the students only. So, have you seen this series? Not in algebra, somewhere else? How do you find? It's very easy to find those series. You use Fourier series. To check the convergence of the Fourier series, if you know about Fourier series, you take some specific, I mean, admissible values of the variable, then you will get this as this. I don't want to go into Fourier series details. If I am left with some time, maybe I will come back. Fourier series, Fourier integral, all those things. Now I am leaving pi there, I come to mathematics. In general, what we think about mathematics, okay? Where do we find mathematics? So now I am totally a salesman for mathematics. So I am trying to sell mathematics as much as possible. That's what I do. Then when I come, suppose I represent a company, first I will talk about all products. Then I will focus. No, actually if you do not want to take at least this detergent. So my detergent will be differential equation. Now I will talk in general about mathematics, then I will talk about differential equation, and I try to tell you, and I will consider myself successful. At the end of the lecture, every one of you should feel that without differential equation, our life has no value. So then I am a successful salesman. Okay. Now where do you find mathematics? Okay, this morning just before coming, I had to go buy something, and the shopkeeper was not present. His young son, he was present. I purchased something which was 650 grams. And that was priced at something, but he immediately said, sir, this much. See his calculation. He knows if it is 1 kg, say 35 rupees, even you people may not be able to calculate how much it will be for 650 grams. But just like that he said. Now, whether we will say that he knows mathematics, yes, that is part of mathematics. You now talk about Uber and Ola, I will not take because they don't do anything calculation themselves. It is determined by their software, so 340 rupees from here to IIT. It's something like that. But you go to the shops, you go to a carpenter, okay? The kind of measurement he takes, he will take square meter and all those things. But they are not like formally educated. That means mathematics everyone knows. But we claim because we have PhDs, we only know mathematics. That is not true. There are many other people actually who are kind of laymen. They have lot of knowledge. So for a rickshaw puller, carpenter, grocer, then you come to the higher ones like physicists, mathematicians, biologists, engineers and all those people. Everyone knows mathematics. But the degree of knowledge is different. The perception is different. What mathematics I need, someone else may not need that mathematics. His mathematics or his actually outlook about mathematics, that will be different. Now, of course, we being academicians, you talk about any subject, physics, electronics, mechanical engineering, computer engineering, civil engineering, ocean engineering, it is omnipresent. I did not speak about biology because when we are growing, madam also will agree, those people who wanted to do biology or medical, they think mathematics is not needed. Throw it out. And other way around will feel, I want to do mathematics, why I want to learn biology? So But now it has been found. Even I have added one of my new research area, mathematical biology, where I am using some fractional differential equation to model some biological problem. There are many people who are working in biology and who actually need to do biological problem. A mathematician does not need to know biology that much. Some basic concept is required. But for a purely biologist to work in mathematical biology, it is very difficult, because mathematics, we have so many terms, so many results and all those things, right? Once I had gone to IIT Delhi, Center for Atmospheric Sciences. There used to be one madam, very senior professor. Then I was sitting with her, and she said, Swarup, I will show you some, what she said, behind their department, I want to show you something. I went, I said, there is a small pond, okay, about this big. Then you have all weeds and all those things. I said, what are you doing? And she is vegetarian. So I'm breeding fish. I said, you don't eat fish? She said, no, we got a very nice problem. About the growth of fish. When it's in a confined region, what should be the area or what food you are providing? So I'm studying. I said, I never knew that you can study on this. How can you do it? So much of, no, I have one postdoctoral researcher who has a degree in zoology. So a mathematician working with a person who has a PhD in zoology. So that shows now how close mathematics and biology can be if you allow. If you do not allow biology this side, mathematics this side, then also you can survive. I am not saying that you have to combine biology with mathematics, but there are many fascinating problems in biology which, when it is expressed in terms of mathematics, it becomes a very good solution. Okay? We talk about growth and decay of species in biology. Without mathematics, I do not know even how they can predict actually what is going to happen in near future. Now, if you ask, I usually do not categorize. I think mathematician is mathematician. There is nothing called pure or impure. I belong to the inferior branch that is called applied mathematics. Okay? When I say pure, if you ask a student who is learning English, what is opposite of pure? Impure, polluted. Okay, I do polluted mathematics. So I am known as an applied mathematician. Okay? So every area of mathematics actually has application. So you don't even have to say applicable mathematics. You simply say mathematics. Like you talk about God. Do you add something else before God? You don't add. God is the supreme power. We only say mathematics. Mathematics is the supreme power amongst all the subjects. Okay? Now, when we say pure mathematics, I am also into that area because I work on theoretical sides of differential equations where I do not solve any problem. I look at the existence and uniqueness of solutions. I look at the controllability. I look at stability. I am not solving any problem. That is one area of research I have added in last 7-8 years. I have about close to 40 publications in that area. So in that case, I am what so-called pure mathematician. Now if you ask me, sir, what you have done, I have read your paper in fractional calculus and applied analysis. I could not understand anything. What is the application? At that point, I cannot say anything that you can apply it correctly, right? But sometimes you get ideas. We submitted one paper, totally theoretical. Even I found it a bit boring towards the end. Okay, so what I am doing actually, whether it is good. Then somehow one of the experts or reviewers said, why don't you try to connect it to some physical problem? And we have good research scholars. So one student actually, he connected it to a circuit, LRC circuit, in electrical circuit, LRC circuit. And that paper, which only had analysis, also got connected to an application. So what I mean to say is that, you may be thinking, no, I am selling the subject or sir is selling himself. I am a great mathematician. I am not doing that. I am just trying to give you some examples. So it's always better to give examples which I know which is true. I cannot talk about someone else because that may not be true. So application will be very, now if he had asked me, now I am that person, Beginning you asked me, what is the application of your result? I said, I will not be able, I may not know. I'm not looking at that, whether there should be some application. We know GH30. We know GH30 because of Ramanujan. Would you have come to know about Ramanujan if this person was not there in this world? No. Ramanujan would not, no one would have known except for his parents and his wife who Ramanujan was. GH30 is the person who got everything out of Ramanujan, and it's very unfortunate that Ramanujan did not stay long. Now Hardy was interested in number theory at that point. No use. You are doing the subject because you like it. We do many things because we like. We don't need to know actually whether that is going to help me, that is going to help someone, or that has some kind of application anywhere else, right? So he was very proud of his area because he loved it. People say, no, mathematics is a beautiful subject. What do you do by that? When I say beautiful, a beautiful girl, I just look at her face, how her face looks like, what is the complexion, then we'll say that is a good looking girl. Okay? Now, beauty is not external. Beauty is how good that girl is as a person. If that has to define her, that has to be the inner beauty. That is what it is about Hardy. He went deep into the subject. He loved whatever contents were there in that subject, and he was in love with that subject, right? He simply did not bother what I am doing, whether next generation, after 10 generations, there will be some application or not. The beauty is associated with female. That's what I talked about a girl. I did not say about a boy, because when you say boy, okay, Bora sir is a handsome person. You will not say he is a beautiful person, right? So it's like that. Now boys should not feel bad, that's what I'm saying. Now it is the inherent beauty. Inherent beauty is not here. Inherent beauty will be inside you. Okay? Now, I am again into the other one. Work in areas which we claim they are more applicable. I am doing differential equation, you are doing algebra. No, your work does not work. It's useless. Okay? That fight goes on. We never fight. Because I respect all areas of mathematics because they are equally important. Now these are some areas actually people say. If those people who are working there do not say, someone else will also say, okay, he is working in ocean engineering, a very practical area. Or that person is working in finance, it's a very practical area. No denying to that, but it does not necessarily mean that. It is like this, na, I love Brahmaputra. That does not mean that I do not like other rivers, right? So it is like that. Now in mathematical finance, there is an equation called Black-Scholes equation, which is the fundamental equation of mathematical finance. Now those people who are doing mathematical finance, they are mostly mathematicians. So now you can see that you need to have knowledge of finance, you need to have knowledge of mathematics as well. A mathematician can garner the idea of finance in a very easy way, but it's not vice versa. A person who knows only finance, he may not know that mathematics that deep. So you need actually, that is what you want to collaborate. A person working in economics is working with a person in mathematics. Like I said, one zoologist working with a mathematician, right? Now, economics. So we can define the physics, chemistry, maths. It is what the madam is the dean of those sciences, no? Physics, chemistry, maths. Why economics is not there? Why sociology is not there? Are not there science? How do you define science? Okay. Sociology. My daughter, she did her bachelor's in sociology from Delhi University. She got a BA, Bachelor of Arts, that is acceptable. Then she went to Netherlands to do her master's. After she got her degree, she sent me the certificate. Is awarded MSc in sociology. Now, whether some subject is science or arts, now political science, what is their science is in political science? Have you ever thought about it? But the subject itself is called political science, but where is the science? Now economics, many people say that you are doing economics, you must be in humanities. Yes, you may be. Now, being a mathematician, I can do an honors in or major in economics without having economics at +2. I passed my 12, I want to do economics, I can do. Now, you don't have mathematics. You have economics, but you don't have mathematics in +2. Most of the leading universities will say, oh, you had economics, but you did not have mathematics. We will not allow you to admit it into economics program. Okay. So you can have, even without having economics, I am allowed to do a major in economics because I had mathematics. You had economics at your +2, but you did not have mathematics, you are not allowed to do economics. So that is how much important your subject is. Now we see, we are talking about Hardy. Now we are talking about public key crypto system. You talk about security, okay? You see secure network security. Okay, you want that your mobile, your laptop should be secured all the time. The huge application of number theory into that. Crypto systems, okay? You know about cryptography. All those things are nothing but the base is mathematics. It may be some computer scientist who is doing, but computer scientist, when you say, he is actually a mathematician, he or she. When you say computer engineer, he or she is an engineer. But when you say computer scientist, those people who do algorithm and all those things, they are actually mathematicians. And you know, computer science actually came out of mathematics only. Now you talk about any area, you talk about engineering, civil, electrical, you want to talk about circuits, you want to talk about signal processing, you want to talk about speech processing, you want to talk about fluid dynamics problem, everywhere you need mathematics, okay? Not necessarily differential equation. Blood flow, I am saying blood flow in medical science, you talk about algebra, and statistics and stochastic processes. You have any faculty in statistics? Oh, okay. Now why I ask, because earlier statistics was a part of mathematics. Now you see every college and university, you have a department of mathematics, department of statistics. Because statistics has become so vast now that you actually do not belong to mathematics, or you are a very big subset of mathematics. So you can come out. So it's an independent subject so that you can have more improvement in the subject. Statistics last few years has got, it's very difficult even. When I asked him, he said, no, there is no, it's very difficult to get a statistics faculty. Even in IITs, we are finding it so difficult to find because statistics is kind of now, or probability you are using kind of prediction. Now you may be happy, I may be happy is what is happening today, but as a businessman, I would like to know something I have started here, what will happen in 2027. You want to make some model. You need some data. You need some model to know actually what is going to happen in 2027. Then only I will invest money, otherwise I will not. But otherwise I will be making losses, right? So statistics is very important. Now you talk about artificial intelligence and data science. You heard about these things? Huh? You heard or not? You don't have to know. I am not going to ask any question. People say, no, I want to do AI. I was thinking first they are talking about they are joining some Air India or something like that. AI. I was not sure. Artificial intelligence. Then data sciences. Of course, data science means you need huge collection of data. You can put it into your modeling. But what basic concept you need? First of all, you have to be very strong in mathematics. Otherwise, artificial intelligence, data science you cannot do. You need to know statistics in and out. So you'll see any syllabus of AI and data sciences, you'll see the huge number of courses in mathematics. Linear algebra, scientific computing, statistics, inference theory, probability, and so on. Many people have started working on artificial intelligence, they belong to mathematics department. You talk about machine learning, right? I am an old-fashioned person, so I don't want to learn anything new. Someone asked me, why don't you do AI? I said, I am intelligent enough. I don't want to become artificially intelligent, okay? Now, someone who works in fluid dynamics, like I do, first, I cannot understand the fluid dynamics concept unless I know what equation is governing the phenomenon. I have to know the differential equation. After that, I have to know some solution techniques. It may be in terms of by using Laplace transform, maybe Fourier series, maybe something else, perturbation technique, I have to know that. Now someone who is working in theoretical computer science. Theoretical computer science is an offshoot of mathematics. And if you do not know, in our department, though it is called the Department of Mathematics, we have about 40 faculty members. We have 8 faculty members who have PhD in computer science. Out of those 8, 7 of them have basic mathematics degree only. They have BSc mathematics, MSc mathematics, PhD computer science. We have only one faculty member who is BTech, MTech, and so what it means when you say theoretical computer science, you are going to computer science with your strong background in mathematics. Signal processing, as well as you add to it speech processing. Okay, I know some people who are working in these areas, they are not electrical engineers. I know a friend who has BSc, MSc in statistics, then he did also what we call this computer degree, MCA, then he did PhD in computer science. So if you see, he does not have a basic computer science or engineering degree, but he is doing very well in signal processing and speech processing due to his background. And one of his engineering colleague who has engineering degree, he said that this fellow is doing better than me because he has background statistics and mathematics. Okay, but many of us, okay, I always include myself so that no one feels bad. So many of us are somewhere in between, okay. So we do not know whether we are into the application side or we are just into the theory side. We try to go forward, backward, both sides, okay. We are on the middle line. We'll be always delighted if someone says, okay, your work is helpful for solving this problem. So I'll be very happy. But at the same time, we are not very ambitious. It does not matter also if it is not of use. Okay? So that's what. We are satisfied. We are happy with something very small things, right? Okay, these are the areas of mathematics. If you talk about broad areas, so these are the broad areas. I said they are under mathematics, or they are the areas where you need knowledge of mathematics. We talk about algebra, analysis, differential equations, statistics, computer science. So I usually belong to the middle group, but now somehow I have also become a small member of the second group. Applications everywhere. Our body itself, lot of mathematics. You talk about blood flow, okay, you talk about anything else. Now see, I have a headache. I go to the doctor. He either gives me a tablet or he may prescribe an injection. Do I get the injection here? I don't get, right? So anything external, I may apply an ointment here, but I am taking an injection here, or I am taking a tablet. After 10 minutes, I am fine. Or 10 minutes, it is only in the advertisements you get good in 1 minute. So it may take me 6 hours or 7 hours to get out of this headache or something like that, okay? Now, you see, I mean, injection is pushed here and it has gone to this place to give me relief. So this is called drug delivery, okay, drug delivery. Now, actually when it is injected, the fluid knows where to go. Now there is beautiful mathematical modeling for that, okay, where you ensure that the drug gets delivered at the place where it is needed in an optimum time. Hardy I already talked about. So as I said, I mean, mathematics is so huge. Mathematics is like an universe, okay? So we cannot talk about every, first thing, I am not specialized enough to talk about every area of mathematics. I am not competent enough. Second thing, there is no end. What area you want to discuss? You want to talk, topic itself is a subject nowadays. Topic itself is a, now I work in fluid dynamics, someone else works in fluid dynamics. I may not understand his work, he may not understand my work. So areas have become so vast, okay? So I have decided to sell only differential equations today. Maybe some other day I will come and try to sell numerical analysis. So this is a cup of coffee. I hope it looks, one is hot, right? It looks like or not? So it will definitely happen for people like me. You give me a cup of tea, I love talking, I love speaking. After 10 minutes only I realize, oh, one coffee was there, then it will happen the second one. It will become cold. So it's simple physics. But you know, those physics events can be expressed in terms of differential equation. You talk about a coin being tossed, right? Heads or tail, you say, it falls on the ground. How far it goes? Someone hits, okay? You see cricket, na? They will show na what is the distance, what is the vertical distance. It's like a projectile motion, right? Then you know about pendulum. This one is a static position. Then when a pendulum moves. So any motion you talk about, it is involved with something called equation of motion, which has to be a differential equation. Left one is called something called sloshing. This is not a very nice example. So what is happening? There is a container, maybe in your chemistry lab, because I saw something colorful. I am very bad in chemistry, by the way. So you have a container, some fluid is kept, okay? You may have realized by now I am a very restless person. I am moving here and there everywhere. I come in and just hit the table. Now what is happening, you see? The free surface of the fluid, it is getting displaced very abruptly. Okay. Now the next one is called aquifer. Okay. So we usually use groundwater most of the places. IIT Guwahati, we are getting the water from Brahmaputra, and maybe in the city also many areas there are so many like water providers. I think Guwahati Municipal Corporation, then there is some water board or something like that. But most of the time we get water from underground. Okay. We have well or we get it from underground, right? So you just try to imagine when you have if you have a well at home, try to see the all water getting concentrated there. It is not happening overnight. So what is happening around the area, whatever soil you have, the layer wise, stratified. So it is porous, so that water can actually, now we have dug a big hole here, so now water is flowing with the slope actually through the pores to the well, and you have accumulation of water. But I think this February, March is the worst period in Guwahati. I think most of the places people are now buying water, right? People in Guwahati buy water. That is a very good example of sloshing. If you see in the city, big trucks, maybe 5,000 or 10,000 liters, and small autos, auto vans with 1,000 liter. Now, you see it looks like it is full, it's covered, but all of a sudden it comes across a speed breaker. You will see water splashing out. That means the free surface actually going up and that water comes up. So there were some baffle, something called baffle is used under the lid so that water cannot come out. So that is a very nice area of research, sloshing. So many laws, you talk about physics, you talk about chemistry. Now I advocate also about biology or astronomy. Most expressions, they find natural expression in differential equations. Okay? So first you go with nature. If you look at the basic laws you talk about astronomy, they all date back to 16th century, 17th century. That was probably the first area of research, astronomy, only because nature you had, no one can stop you from accessing nature. Nature is free. I can go outside, nature is available, right? But I want to go to a movie theater, some INOX. I am not allowed to go inside because I have to pay. So I cannot do any research in INOX or Inox, whatever you say. You people go for movies, no? So, but I'm free to have nature. I can look at the sky, I can see the pollution, I can see whether the sun has come out or not. No one can stop. So that is how it is. You talk about ocean, lake, rains, clouds, whatever you do, that is your part of nature. Now, astronomy, as we know, since it was your first available subject for people to, otherwise what people would have been doing, I am just wondering. Now you people can be busy, you have mobile, laptop, Facebook, Instagram, everything, it can keep yourself busy rather than your study. Na? Think about 16th century, 17th century. What you do? You have to do some work for your livelihood. Maybe you go to the woods, get the woods, then hunt some animals or something like that. Beyond that, what you will do? And that is what I think most of the things could happen there. And now we have everything, so we cannot expect that we can find anything fundamental now, right? Our life is very easygoing. We don't have to do anything. Everything comes on its own. Now, when we talk about satellite, we know the moon is a natural satellite of the earth, but we are not bothered about moon because moon is already whatever millions of years it is doing, it is doing. There is no danger that moon will go off its orbit and fall on us or something like that. No? So now, looking at how moon revolves around the earth, now how you are getting all those TV channels, everything, mobile, internet, connectivity and all those things. It is through artificial satellite. Right? You have communication satellite. Now I know our Pakistan will be spying India, India will be spying Pakistan. You have your these defense satellites. Then so many other satellites are there. That is possible because it's a huge work. You just see, you are sending something from here, then you expect that it will take an orbit and revolve around the earth. Okay? So that is what the greatness of the scientists are. When we say scientists, it is not that it is not engineers are included. Scientists are actually those people who work at a higher level. Now when you talk about ISRO, you talk about DRDO. The team is a collection of like mathematician, physicist, communication engineer, computer engineer, mechanical engineer and so on and so forth. Right? Now, I am telling stories now, so I'll tell a story. 1975, I think first artificial satellite was launched by India, Aryabhatta 1. So initial time they found there is a flaw, and now you see there is no high-end computer at that time. It is about now 40 years back almost. Then they found that if they are going to put it on the orbit, probably it will not work. Someone said there is some flaw in the governing equation with the inclination. Then there is one Professor K.B. Bhatnagar from Delhi University. He works in space dynamics and he knows a lot of things about space. He was called, then he was asked to look at the problem thoroughly. It is small, something minor, but he actually rectified that. And that's how Aryabhatta actually could go into the space. Okay. So what I want to say that there are many other people, but ultimately it is a mathematician who had to rectify whatever they were doing. Only I am given tea, sorry for others. So, river flow, I think that season is over. I think last month, January, all of us would be very tempted to go for picnic. But if you go for picnic, which one you will prefer? First one or second one? Elderly people will like, okay, second one is fine. The young people, oh, first one looks, oh, we'll do rafting and all those things, right? So whatever you do, the second one is a bit quiet. But it does not mean that it is not moving. Still it is moving. It's a slow speed. But if you look at the first picture, it is moving at a faster speed. So equations of motions are involved in both. Basic equation of motion will be same, but ultimately there will be certain condition actually which will make the problems different. Now we will like one of them. If you ask me, though I am an old person, I like adventure, so I will, as a picnic goer, I will prefer the first one. But if you say that, sir, you do some modeling, I say, no, I don't like that. I will come to the second one. Because there is something called linearity and non-linearity involved. Okay? Your life is linear, means straight line. Okay? No variation. But your something is like this wavy, right? That is non-linear. So all of you know that linear problems are easy to attempt compared to non-linear problems. Of course, there are many non-linear problems which can be converted, but it's not that easy. So, as a mathematician, as Mr. Bora, I will prefer the first one. As Professor Bora, I will go for the second one. Now you know in the border of US and Canada, we have 5 Great Lakes. Okay. Now these lakes are so big, they are almost equivalent to sea. If you had done geography, you must have seen there is something called Caspian Sea in Russia. It's not a sea, it's a landlocked, right? Why it is you call sea? That it exhibits all the properties that actually one sea exhibits, like the creation of wave, the kind of erosion that it happens on the beach. Okay, so these are also dull layer lakes. So now you look at the second picture I brought in because I found it very beautiful. You see, it's like snow-capped mountain with its reflection. But now if you look at the water level, still water level, there is no displacement at all. Maybe some displacement is there which is very negligible, right? Famous Niagara Falls, you must have heard. If you have not gone, you study well, you will be able to see it yourself. I was fortunate enough to see both sides. I went once because I did PhD in Canada, so it was not difficult for me to go there. One I visited in summer, you see the floor, left one. Other one is actually there is no motion. Vertically if you see, they are all ice. You know, December, January, how cold those regions get. Now the mathematics that is involved in the first figure, same thing, same Niagara Falls, which has been flowing for thousands of years, millions of years. But when you look at the mathematics component, what mathematics you apply to the first problem will be different from the second problem, though it is the same falls you are talking about. You know, change in life is very important. Change in everything is very important. I am not making any political statement. You don't bring it to change to Parivartan or something like that. I am not talking about that. I am talking about, rate of change of physical quantity. Okay? You talk about a curve or you talk about anything else. Change is inevitable. Okay? If there is no change, what is that? It's very boring, right? Otherwise also, it has to change. Now you are growing. You were born, you were a baby, then you became a little grown up, then you became adult, right? So now, rate of change, physical sense also it is very important. There is some event which is actually related to some change, and that gives you a differential equation, right? Because most of the natural processes will have some kind of change. My time is till 12, no? I thought you gave me 1.5 hours, that is too long, but I think I can speak for 1.5 hours, it seems. Huh? I still have that much energy. Now, simple examples you look at. Newton's second law of motion. When you studied in school, it's simply a formula like force is equal to mass into acceleration. You want to find any one of the quantities if you are given the values of the other two quantities. But that does not tell you everything instantaneous. That tells you fixed value. F you are finding by some, m is anyway constant, acceleration that is not varying, force which is not varying, right? But now you want to make it instantaneous, that you want to study the displacement at any instant, at any t that you want. So if you talk about a mass falling freely, I drop something like this. I should not drop this. I could have dropped if it was not mine, maybe. That's what people feel, right? But this is mine, so I will not drop. So if I drop it, right, so it will fall on the floor, right? Now, that we know how much time it takes. Just look at your watch. Oh, it took 1 second or 1.2 seconds, okay? You don't even have to measure. I know how much it is, 3 feet or something like that. But someone says, no, I want to know how much time it has taken to reach this point, okay? Or someone may say that how much distance it has traveled in half second. So then it is very difficult. All the time you cannot do the measurement. So you need some solution which gives you the information at every instant. Any t you want to put, you should be able to find, okay? So when we say y is displacement, of course, dy dt is the velocity and d2y dt2 will be your acceleration. You put it back. M is fixed mass. Now my acceleration depends on time. It is time specific. So d2y dt2 is equal to force. But here I have not applied any force. You see, I have simply released it. mg. mg is the force. So your differential equation is the m d2y dt2 equal to mg. M you can cancel. So this is a very simple second order differential equation. But same phenomenon, I can have another differential equation. Can you tell me how can I have another differential equation? I did not consider any resistance. Because you know every force has its opposite force also. No? Every action has a reaction. That is also Newton's law. So when something is getting dropped, actually there will be an opposing force from the bottom, which will be due to mainly air resistance. So if I add that, your differential equation gets changed because your air resistance is proportional to the velocity. Now my simple differential equation gets changed to this differential equation. So when we do not have the air resistance, it is called an undamped motion, and when air resistance is taken into account, it is called a damped motion. Now that is what I started with the first slide. T becoming colder. Now I have learned from Newton's law of cooling, so I am standing near to my tea, it is not getting cold, right? Now Newton's law of cooling says that the rate of change of temperature of any object is proportional to the difference between the instantaneous temperature and the room temperature, or the room temperature of the surrounding. So this statement, when you convert it, it becomes the simple differential equation. When you are saying cooling, you are giving away, then you write minus. Now heating is what? Heating is opposite of cooling. So then if you are talking about a problem of, though law says cooling, you can make the sign change and it becomes a example of heating. So two cases, like I am saying tea getting colder. The opposite thing what happens? You have that cone ice cream I showed you. You have a cone ice cream. But here's something important to discuss. You started talking. After 5 minutes, what happens? It gets melted. Now that will be actually Newton's law of cooling in the sense of heating. Because when tea you are talking about, it is giving away heat. But when you are talking about the ice cream, it is absorbing heat into the system from the surrounding. I am halfway through only, so I have to finish it quickly. I am playing like a Cheteshwar Pujara. You know, you follow cricket or not? No, Cheteshwar Pujara plays very slow. So I am now play like Subman Gill. So similar way, if you talk about a pendulum, motion of a pendulum, this is the differential equation you get. But you cannot solve it immediately. Why you cannot solve? It is a nonlinear equation. It's not that you have theta, you have sine theta. So nonlinear equation is very difficult to solve. Now you say, okay, this is nonlinear equation I cannot solve. I am not capable of solving. I make it linear, simply throw sine out. You cannot do that. You can make a nonlinear problem linear, but you have to have some assumptions which should make sense. Now you know when is sine theta, you can write as theta. When theta is small, sine theta can be replaced by theta, right? So now if you consider the motion of a pendulum motion will not go like this, na? So it is the equilibrium position, it will go like this. So you can consider the theta to be small. In that case, what you can say, that sine theta can be replaced by theta, so that a nonlinear equation becomes a linear equation and you can find a solution. Now we talk about planets, you talk about star. When we talk about planet, usually we think that it is solid kind of thing. It's not true. We have many stars actually which are full of gases. They are gaseous stars. So that means what happened? Gas is something which is compressible, right? You can compress. That means when you have a gaseous star, its volume may not be same. Its mass actually may fluctuate because you know due to pressure and all those things, gas will change. So it's a big star, gaseous star. So otherwise I cannot write dmdr. Usually you consider mass to be constant. Now what it says here, mass will change with respect to the radial distance. A very simple differential equation. That means the gaseous stars also follow some differential equation. Now we are talking about satellite. We know that the satellites will take some orbit to revolve around the parent planet. In this case it is the Earth. Okay? So this is a system of differential equation that describes the motion of a satellite. It's a system of equations. You see, it's not only one equation. If you see the second derivatives, they are with respect to x, y, z. Right? X, y, z means basically you are considering three-dimensional motion. So you have three axes, then you are talking about the acceleration term or the force term along all the directions. Now again I have talked about this mathematical biology. There are some models, predator-prey model, okay. Then there is some general model which is called Kolmogorov's predator-prey model. So they are very simple differential equations, but they actually depict some very important practical physical applications. Now, as I said, we have a big river, right, Brahmaputra. Actually, you know, bigger water bodies, it is easy to study. Smaller water bodies, is very difficult to study. Because big water body, what happens? When I talk about ocean, I can say, no, that is infinity, that is infinity. That makes it easier for me. You talk about Brahmaputra, if you go to Dibrugarh side, you cannot see the other side of Brahmaputra. If anyone is from Dibrugarh, I do not know. But Guwahati, you can see the other side. From here, you can see IIT, right? That means width I have to consider. But Dibrugarh, I can say, no, I cannot see, I will not consider width. So I consider only one dimension, x, or maximum the depth z. But Guwahati you have to consider z, x, y. That makes my problem complicated. Okay, but it's very interesting in river mechanics. Most of the problems are one dimensional. You consider only the x direction, but of course, which will change with respect to time. So these are the things can be discharged, how much flow is being discharged, what kind of flood may happen, okay, how kind of erosion can happen, river mechanics. The main tools are mathematics. Oh, it's not that I have put the mistakenly or something like that. What I want to say is, do you recognize this place? So what you recognize in the whole photo, only one person, right? Okay, so that is me and my wife. So we had gone for a picnic to Bogamati. 4 families, all husband, wives, okay? Then I was looking at the river. So if you see this portion, flow is a bit high. So it was actually here. Then this is somewhere the source, okay? Now I got very fascinated by two things. If you look at this river, this part, flow is very quiet. If you look at this part, it is a bit non-linear. And this one you see, it's actually artificial, it is called canal. So what they have done, because water is aplenty, they want something for their irrigation, they have actually designed some canals. Now, these canals, you see width is very less. But the way it is flowing, it will also depend on the main flow and also the slope of the bed, how it has to come. See, it should not, they have just dug in. They have to follow some scientific principle, then only it will flow. And what kind of rocks and sands actually have eroded into the canal and all those things. So I got lost for half an hour and the signal was very bad. So they thought I fell into the river or something like that. I come out after half an hour taking some videos and pictures of this river. I got scolding, that's a different issue. I got a scolding, but next month one of my students is going to get a PhD because of these photographs. She said she wanted to do some river mechanics. We started the problem. But I was not being able to realize, because if I go to Brahmaputra, I get lost. It's such a huge river. So I went there, we had some confusion. We looked at the video again and again. We looked at the pictures again and again. And this girl, she is very good in mathematics, very strong analytically. Now, I think another 12 days she is going to give her synopsis seminar. Next month she will submit. So what I am trying to say is that you should not feel, I am not a boring person. I am very actually witty person. People enjoy time with, because you may think, oh, he has gone for picnic, taking picture here and there. Instead of taking picture of those nature, hill and his friends, he is taking those things. So what I mean to say is that it's always better keep your ears and eyes open. Okay? Mouth, of course, my mouth is open all the time. The 1.5 hours I am speaking already. So I am actually opposite to the 3 monkeys of Gandhiji. Gandhiji said in a different aspect. But I feel, I tell the students, you keep your ears open, keep your eyes open, keep your mouth open. If you have any confusion, you straight away ask your teacher. So I have another set of monkeys which behave exactly opposite to Gandhiji's monkey. Okay? So I just wanted to show something, chemistry, because that is a subject. I got very good marks in my class 12, but I could never like the subject. I'm very sorry if someone likes chemistry. I'm not saying that you should not like. It was very late for me to realize. Probably I would have loved chemistry more if I knew that there are some differential equations also. We always talk about the chemical reactions we see in the lab, what we are doing laboratory, we get the reactions. But we talk about first order reaction. You talk about second order reactions, they are nothing but some ordinary differential equations. So this you see, you are talking about some species which has an initial concentration A, it reacts with something, produces another product whose instantaneous concentration is your X. So this is a very simple first order ordinary differential equation. Now you get encouraged. I said, why 1? I will add 2 of the species, get a third one. Okay? So you combine A and B, which becomes C. This is also a first order equation, but it involves the information of the initial concentration from both the species, capital A and capital B. You get more encouraged. You add A plus B plus C, plus D plus E plus F plus G, and whatever you add, that will also be a first order differential equation only. Only you will see that the product terms will get increased. You consider 3, there will be another C minus X and something like that. I then realized if we had been told these things when we were students, probably we would have studied. So these are something about electric circuit. If you see when you are looking at the lights, okay, there is no fluctuation. Okay, that means the voltage supply is very, stable. Voltage supply is stable, then only you get a very stable electricity. Either the voltage has to be your constant or it has to be sinusoidal. Okay? So we know that the rate of change of charge is given by current, and this is what your Kirchhoff's law, it talks about the voltage. You take the algebraic sum of the voltage, which should be equal to the quantity, which is your electromagnetic force. That is what we call as EMF. Okay? So this will be a simple differential equation, and there can be 2 types, as I said, constant voltage. Then you have a periodic voltage. Now we should think that constant voltage is already there. Why we are bringing periodic voltage? Periodic voltage is stronger in the sense that it may change, but it is very, you know about the definition of a periodic function. So we talk about sine and cos. It's very nice, very well behaved function. So instead of constant voltage, if you have a periodic voltage, then actually once your EMF is periodic, the current also becomes periodic, because you are using that value of EMF in generating the current. Second order equations, plenty of uses. This is the spring mass system. As you see, there are 3 terms. First term is due to the force itself. Second term is the resistance. Okay? When you are writing the right hand side, 0 means you don't have any applied force. In the second equation, in addition to all these terms, you have also applied some force, which is a periodic force, because you see the presence of cosine and sine. So first order equation that we had in terms of electric current, because current is the derivative of Q with respect to T, you put that here, then it becomes a second order equation in current. Now I think I am feeling tired. So now you look at this equation, it's a fourth order equation. Usually we talk mostly about second order equation. But you ask any of your friends who is doing civil engineering, whether he or she has seen this equation or not. If he or she says yes, that's good. If he or she says no, he or she has not seen, what you will do? I have asked, you don't study civil engineering. Because without this equation, you cannot learn civil engineering. This is called Euler-Beam equation. Now you feel comfortable or not? This is first floor, of course you will feel comfortable. You go higher up in the building, you feel comfortable or not? Comfortable in the sense that you don't have any fear that this building may break or it may collapse. You have the full confidence, because when you talk about the construction of a building, you look at the beam, how strong the beam is. If the beam is constructed properly, the whole building will be very safe, and that is governed by this equation. Actually, fourth order equation, I do not know whether those laborers, masons who do the beam, they follow this or not, but I am sure those who supervise, they know actually, because when you are talking about beam means what? You have some rods, then you do it cementing around. Okay? So there has to be some space so that whenever some displacement happens, okay, some compression happens, it can take it. Biology too much we are doing, we will not do biology. I have many slides. I will just, I know you people will be, you love to see some pictures, no? I will not talk about anything research, but this is what I started my research with, which was very accidental. When I went to do my PhD in Canada, my supervisor, I asked, what is the topic? I was very serious at that time. Nowadays, I am not serious. I want to do research. I have come so far from India. Give me a topic. Say, relax, relax. You have traveled so much. You just go around. You have some friends. It's a nice place. You go around. Go around means Halifax is a small city, port city. Every day I go to the ocean only. Ocean, the shoreline, it is lovely. I see these waves. Then I saw these big, big vessels, ships coming, loading and all those things. I got very much interested in by this ocean. Then I told my supervisor, I will work on ocean engineering if possible, mathematical sense, without going into the ocean, because it's very scary, the waves that it gets created. Then supervisor said, yes, I also wanted you to do that, but I thought you should come yourself. Now you look at these pictures. I always go by the beauty. All of us will go by beauty. So you have decided to go to Kovalam or Goa or somewhere like that. In order of preference, which picture you would like to see? Definitely first one. Even if you do not do surfing, but if you see a wave like this, it's a lifetime thing that you have seen a wave like this. Look at the second one. Second one means this, but it looks a bit gloomy. You never know actually what is waiting for you. You look at the sky. Okay, this is the warning kind of thing. Something like very, strong hurricane or maybe tsunami is on the way. I would have loved to face these two situations. Again, I will say, as Mr. Bora, I like to face the first two situations. But I become an academician, Professor Bora, I like to handle the below ones. Because you talk about linearity, non-linearity, first two are very highly non-linear, but the bottom two figures are linear. So, as a person, what you want, and in your profession, what you want, it differs. That is very painful sometimes. You know about Bombay High. So there are some platforms with the help of which actually you extract oil from the sea bottom. It is everywhere. In Mexico it is there. You have in North Sea near UK. Then nowadays I see Norway, Poland, all of them are actually doing that. But you see, you see four legs, no? Four fat legs. 1, 2, 3, 4. It's like a chair. 4 legs. Suppose it is located at a depth of 4 kilometers. Not at a depth, at a place where the ocean depth is 4 kilometers. You cannot expect that all the 4 legs will go 4 kilometers into the seabed. So there is something called tension leg platform. There is some tension, you know about tension, no? Not in your life tension. I am talking about tension in the string when you talk about a force. That tension, okay, that actually makes the legs actually maybe few meters only, but it is stable. Now you see the wave that comes and interacts. It will be a huge amplitude, it will be a huge force. Now, as an engineer or as a mathematician or as a practitioner, what you want? You want that, we want the structure to stay there, but we want that it is stable. Beautiful mathematical modelings are there actually, in terms of partial differential equation. I have close to 80 papers in ocean engineering. Ship, okay. You know how Titanic sank? It hit a iceberg, right? Otherwise everything was going fine, right? Now, this kind of cruise ships actually, they travel very long distance. Sometimes it may take months. Now what is happening here? If you are on the beach or on the shoreline, you are looking at the ocean, you only see the waves created by the ocean itself, maybe due to wind or something like that. Now once a ship or boat is moving, there is another wave getting created because the ship itself actually creates another wave, making the mathematical problem challenging but very interesting. Now there is some pollution problem, oil spill. So you know the vessels that bring crude oil. Now you know India, we are not self-sufficient in petroleum. So you easily bring our crude oil from either from Saudi Arabia or Iran, and of course from Russia. Right? But Russia, I mean, route is very long, I think. Now the vessels that they bring, when they face hurricanes or something like that, sometimes there is a possibility that the sloshing I talked about earlier, due to that actually some amount may spill into the ocean. Now, once it has spilled, I cannot do anything, you cannot do anything. But what you want? You want to find a mathematical problem solution such that you want to control the spread. You want to control the spread within a area which is actually acceptable to it. This is basically a way we are talking about some applications. So one of the pictures, I think the fourth picture I used in my slide top. So this is a floating airport. This is a dock or port. And you see this is something constructed, and here we have constructed something like this. So what happens? Ocean as such, inherently it is non-linear. But when you want to have some activities along the shoreline, you want to control the wave in some sense. So how we do? You want to mitigate or you want to dissipate the energy that is coming. So now see something is coming and hitting here. It is not there, it is coming directly hitting me here, right? Suppose I am the structure you want to save. So you will introduce some other structure in front of that so that actually the wave action, its potency is absorbed by this structure so that whatever is coming inside, I am safe. So you are doing actually this tranquility zone. These are all tranquility zones so that the big vessels can come without any difficulty and they can carry out their own work. This is one modeling I have done. So this will be the last. Oh, I watch a lot of movies, so movie things also came. I hope they are connected to it. Okay. So you look at this structure. You know about windmills. India, it is not very popular, but if you go to Europe, you will see many countries, like especially Netherlands, France, Belgium, Poland, they use windmill to actually generate their electrical energy. What we got as hydroelectric maybe from, what is that? Umturu or somewhere like that, or Subansiri or something like that. Now, the small places like in Taiwan, Netherlands, you know, they are very tiny countries. So if they are having a series of windmills on land, they are losing a lot of land because around that area you cannot do anything. So what now they have started doing, they have started erecting the windmill in ocean water, which is more or less free. Of course, they need a lot of clearance from different tribunals. That's a different issue. Right now, actually, I have two collaborators. One is in Poland and another was in Norway. What they are trying to see, they call it as green energy. Now, windmill was already there. So what is so nice about it? You have just shifted it from here to there. Now, what they are trying to do, wind energy you are capturing through these blades. Now, you just imagine about ocean. If suppose a small river can generate electricity, you think about ocean, wave. So much wave all the time. You don't even have to do, you don't have to generate. It gets generated itself. You try to capture that wave. So on top you are capturing wind energy, and at this level you are capturing the wave energy. So it is 2 in 1. You have a structure which captures wind energy as well as these are the non-conventional energy which will be very much needed for us in future. Now another set of persons came, no, we want 3 in 1. How do you make it 3 in 1? 2 in 1 itself is so great. Now they want to do some fishing. Fish breeding, not fishing. So what they have done, already one structure is there, they would surround it with some thin wall with some admissible material so that they can have some kind of aero generators and they can actually breed fish there. So now that has become 3-in-1. And unless they are modeled nicely mathematically, you cannot do anything. When you looked at the problem, it looks so difficult, but when we try to do it mathematically, I simply have to consider a structure like this. Okay? So you have inside one rigid cylinder, this one, then there is a small, there is a thin cylinder of porous material and water is inside. Okay? Now I do not need to consider what is at the top because I want to consider about the wave interaction with the structure. Okay? Now this actually has got very good acceptance. So it was published in a journal published by American Society of Civil Engineers. Okay? Now there is another problem. Suppose you are talking about another fluid flow problem. You have some step-like bottom, then you have some structure, and you want to study how the structure, a wave interacts with this. So these are porous regions. So when wave comes and interacts, it goes into region 4. The potency of the wave is already controlled. Now anything else you have beyond that, that will be protected. Okay? I am almost towards my end. So wave is coming, hitting the structure. You see, some waves have started through. They have gone through the structure and some got reflected. So whenever you talk about wave, if there is an obstacle in between, you have two kinds. One is called your reflection, one is called transmission. So when you study water wave problem, it is very important to identify these quantities, evaluate them, and you try to quantify them. Because when you are telling a practitioner, I say this is what is happening to reflection, increasing, decreasing, he will ask me, tell me the value. Tell me the value of the frequency of the wave. Tell me the value of the porosity of the structure also. So we have to have parametric studies. I put different values of porosity of the structure, then I find, okay, for this value of porosity, wave is getting controlled more. So I have to tell him the porosity. Because practitioner, they will not go with my mathematics. I have to provide the results from my mathematics to them. Oh. So there are movies with mathematics. So mathematics is, people say it's a very boring subject, but it's so good that you can make good, great movies, right? So I hope you have seen this movie, not because it involves mathematics. You should watch this movie. You know about the great mathematician John Nash, who actually, we recognize him later. He got Nobel Prize in 1994 for economics. But the Nobel Prize, the highest prize of mathematics, was given him after 21 years, 2015. And unfortunately, one day after he received Nobel Prize, there was an accident in which he passed away. That is about John Nash. But if you watch the movie, the way Russell Crowe, he has acted. Okay, beautiful movie you should see. And now you must have seen this year all those Oppenheimer, no? It's about physics, but I always think physics and mathematics are same. I mean, two sides of one coin. So if you want to know physics, you need to know mathematics and vice versa. And Oppenheimer, anyway, I think they won some 8 Oscars or something like that. Then of course, no lecture ends without mentioning great Ramanujan. This is one great movie. If you have not seen the movie, at least read the book. The Man Who Knew Infinity. Okay, so this is also a very good movie, and I don't like Dev Patel, but I think he has done well in this movie. Foundations and pillars. I usually, when I stay in a village called Amingao, located on the north side of Guwahati, okay? So when I have to come to city, I have to cross the bridge, right? Few years back we had only one bridge, now we have two bridges, one way. But I don't like the new bridge. I don't trust, because the Saraighat bridge, this is the one, 1962, plus 62 now. 62 years of, year-old bridge, the way it is serving, because the foundation is very strong. You look at that opera house in Sydney, or you talk about Qutub Minar. Nowadays people are not allowed. I think it was constructed in 16th century. It is still standing tall. You just imagine how strong the foundation is. So in your life, you want to be successful, you cannot learn anything arbitrarily or abruptly. First you have to have a very good foundation. Once the foundation is good, stand on that foundation, no one can actually displace you from there. So that is very important in life. Mathematics as a whole, it's not just like about a subject which everyone has to pass, okay? It gives you the analytical thinking. I told you about one of my daughter being specialized in sociology, but one of the subjects she loves is mathematics. Not because her father is a mathematics teacher, but she says that learning mathematics has lent her analytical thinking, systematic approach to all the things that she has been studying in sociology or psychology. So it is not that only science people or engineering people need mathematics. I have a very close friend who is a very good historian. He said because he writes good books, he has contributed, he said that it is because he had mathematics in class 2. It's very difficult sometimes, but I feel very happy when people say that. Gauss, mathematics is the queen of science, arithmetic is the queen of mathematics. Oh, no one talks anything about king. Is it like that wives are always given higher? That is true actually. No? We respect women. We are not saying king is the most powerful. So ma'am is maybe more powerful at home than her husband. Maybe I am not that powerful at home. Maybe my wife is more powerful. That's why we talk about queen only. That's what I want to add, Gauss, that mathematics is the queen of science, arithmetic is the queen of mathematics. So I come to the next generation. I am not going to a prince. I am going to a princess. So I feel differential equation is the princess of science. Without differential equation, you cannot do anything. Okay, so I said, Gauss, there is another interesting story. Gauss, I said, Göttingen. Then the graveyard is open to all. Anyone can go. But you know how you have to pay respect to Gauss? You are supposed to go with 2 bottles of beer, drink 1 beer yourself, and dedicate the other one, Gauss. You dedicate to him, you are supposed to drink both. So you are drinking with Gauss actually. That is what the people celebrate the lives of outsiders. Thank you.
Memorization contest. So before that, I would like to express my sincere appreciation to our distinguished keynote speaker, Professor Dr. Saurabh Nandan Bora sir, Professor at the Indian Institute of Technology, Guwahati. His outstanding presentation not only captivated our audience, but also played a pivotal role in making this event both interesting and meaningful. A special note of gratitude goes to our esteemed Dean, Professor Dr. Anuradha Devi ma'am, for his unwavering support and guidance throughout the planning and execution of this event. I would also like to thank to all the faculty members of the department whose dedication contributed significantly to the success of this event. A heartfelt thank you to the IT department for providing uninterrupted technical support. Additionally, especially I want to acknowledge the initiative and hard work of the students of MSc second semester, students who played a crucial role in the preparation of the World Magazine and supported the smooth conduction of this event. Thank you all, and I wish a great day ahead. Thank you so much.